Hi everybody, it's Camille at Physiology for Hippies. This month we are looking at the blood vessels, and today we're going to talk about how arteries and arterioles affect blood flow. They actually do a lot more than that, but that's what we're focusing on today. Before we start, I actually want to show you one of my favorite things on the internet. And this thing is called Zygote Body. You can see it's at zygotebody.com. And this is essentially a tool that lets you zoom in and out of the different layers of the human body. And I love it. I think it's really cool. And I just wanted to show you a couple things about the cardiovascular system, since I'm showing you this tool anyway. And you can also rotate through the body. So here you can see we've got the heart. And what I want you to look at here is this large red vessel that's leaving the heart. This is the aorta. And this is essentially when the heart pumps the blood to the rest of the body. It's all starting out in the aorta, and it travels from there everywhere in the body. So the aorta has to have extremely high pressure in order for the blood to have enough oomph to reach every single tissue in the body. Okay? And because of that, the arteries need to act as a pressure reservoir. And by that I mean, if all you have to rely on is the one pump of the heart, and that single pump is supposed to distribute the blood everywhere, that's putting a lot of eggs in one basket from the body's perspective. So we need to have a way to somehow hold on to that pressure and maximize it a little bit. And the arteries are conveniently set up to do that. We looked at in our previous video about the structure of the arteries and how they have a lot of musculature there. And one of the things that happens is that when the arteries are exposed to the high pressure, especially the aorta is exposed to the high pressure from the pump of the heart, they expand, okay? Just like a rubber band expands, or if you were to blow into a rubber band, it expands with the extra pressure. All right, and then the arteries are going to slowly come back to their normal size. And as they come back to their normal size, that's going to increase the pressure in the vessel as well, giving the blood a little extra push to get where it's going. And that's why we call it a pressure reservoir. It's that process of the blood vessel expanding under pressure and then slowly coming back to its normal size. So that's really important. Blood pressure in general is a whole nother can of worms, which we'll talk about later. But blood pressure, we need blood pressure to be high enough to get the blood everywhere it needs to go. However, when it's too high, we start to damage our tissues, and that's, like I said, that's a different video. Now, there are two big factors when it comes to the blood vessels that affect blood pressure. There's actually a bunch of other things like hormones and so on and so forth. But there's two big blood vessel related things we need to know about. One of them is this concept of compliance, and that is what we were just talking about with the rubber band. When a blood vessel expands under pressure, that's called compliance. It's a compliant blood vessel. So it's easy to stretch, and then it comes back to center. Just like if you're blowing up a balloon. Usually if the balloon is properly made, when you blow on it, it's easy, it's compliant to blow up, and then if you don't tie it off in a knot, it comes back to its normal spot. When blood vessels lose their compliance, when arteries aren't compliant anymore, then things don't work as well. Blood pressure actually increases in the arteries when the blood vessels are stuck, when it's very hard for them to expand. But the pressure reservoir is lost, so it's harder for the blood to reach distant tissues, and even though the pressure is higher in that artery, if that makes any sense. The other factor that can affect blood pressure that's related to the blood vessels is resistance. And this sounds kind of similar, but it's actually a little bit different. So resistance is when the blood vessels themselves decide to constrict or dilate, not based on, not just from the force of blood flow, but because the tissue that they serve needs more or less blood flow. We're going to talk about that in a little more detail. Now, just as a brief review, I know some of you, this is old hat for you, but for others of you might want to review. When we're talking about blood pressure, we measure it usually in two numbers. The systolic pressure, this top number, is the blood pressure when the heart is squeezed, when the heart undergoes systole or a pump. And then the diastolic pressure is the pressure at rest. So related to what we were just talking about, compliance, how stretchy the arteries and aorta are, is what mainly affects blood pressure in the systolic number. So when compliance goes down, which happens with age or atherosclerosis, hardening of the blood vessels, then your top number, your systolic blood pressure, tends to go up. Okay? The resistance factor down here, which is usually the arterioles are constricting or dilating to change resistance. When that number changes, it actually affects the diastolic pressure more so than the systolic. So the bottom number tends to be affected. And that's, that's an interesting little tidbit to know if you're having some problems with your blood pressure. Okay? Now, here's a little review of the blood vessels. We talked about this in our previous video. And what I want to go into now is the arterioles and how they affect resistance. So if you remember, the arteries are the big blood vessels, and they're the ones that are very compliant, and they stretch and contract just based on how much pressure and flow is coming through them. But the arterioles are the ones that essentially dictate blood flow into specific tissues. And this is where we're going to be focusing today. Now, what regulates blood flow? Let me just move this up a little bit so we can see the whole picture. There are a couple of different things. One of them is sympathetic tone, which we're going to review in a minute. There are hormones that can change blood flow throughout the body, either by interacting with receptors at the arterioles or elsewhere. The endothelium itself, so remember this is the layer of cells that line the lumen of the blood vessel. We have a whole nother video on that. Or metabolic factors. And what I mean by that is, if this, let's say this is an arteriole, and it is leading into skeletal muscle, and you're exercising, you're out on a run, you're working, that skeletal muscle is undergoing a lot of metabolic processes, and it's producing more waste than normal. And so what happens is the waste products, carbon dioxide among others, will start to build up in the tissue around these arterioles that are serving the skeletal muscle. And those metabolic factors can actually cause this particular arteriole to dilate. And what that does is it brings more blood flow. When this blood vessel gets wider and opens up, more blood comes to the area because the skeletal muscles are like, hey, somebody bring us more oxygen and get rid of all this waste product. Okay, so the metabolic factors can actually change blood flow as well. Now, what I actually want to talk about more specifically, because this is something that often confuses people, is this sympathetic tone. So hang in there. I know this is kind of an intense lecture, but I think it's hopefully going to be helpful. Now, as a review, the sympathetic nervous system is activated in quote fight or flight situations, and the parasympathetic nervous system is activated under rest and digest conditions. Parasympathetic nerves don't really have a big effect on systemic vascular resistance, meaning contraction and dilation of the blood vessels at a body-wide level. That's because most of the blood vessels aren't innervated by parasympathetic nerves. So the nervous system just doesn't go there. So basically it doesn't matter if you're resting and digesting, that's not going to be a huge factor. The one major exception to that is in penile erection, but again, that's a different lecture. However, the sympathetic nerves do go to the blood vessels throughout the body. And what happens is at this synapse, this junction here where the nerve connects with the muscles surrounding the blood vessels, norepinephrine is released. So you can pretend these little molecules here are norepinephrine, and it travels across the synapse and binds with receptors. And which receptor is present on the tissue affects what's going to happen. So when when you have alpha-1 receptors, the blood vessels are going to constrict. And this is what most of the blood vessels have. So most blood vessels, when you're in fight or flight mode, are going to get more narrow. Not all of them. Some blood vessels have beta-2 receptors, and in that case, they would dilate. So the blood vessels that tend to have more beta-2 receptors are going to be things like skeletal muscle, because when you're in fight or flight mode, the muscle needs to be moving in case you need to to flee. Okay, same thing with the heart and the lungs. Those are going to be getting more blood flow under fight or flight, whereas most of the other tissues in the body are going to have restricted blood flow. So it all comes down to what receptor is present where. Now, this next part, if you are already like, help me, just put your fingers in your ears for a minute here and just skip this next slide. If you want to go the next level deeper, then let's talk. So some of you might also remember that the adrenal glands also secrete epinephrine and norepinephrine as a hormone, meaning those two things can come into the blood, the vascular system. So instead of traveling via nerves and being released, releasing neurotransmitters at the synapse, you can actually release hormones from the adrenal medulla into the blood. And in that case, you're mostly looking at epinephrine. But epinephrine can travel through the bloodstream and have some similar effects under sympathetic nervous system stimulation. However, in this case, epinephrine is actually, it has a greater affinity for what we call beta-2 receptors. And essentially at low doses, epinephrine is going to cause a mix of vasoconstriction and vasodilation. So it doesn't have as much of an effect on systemic resistance as norepinephrine does. Okay, so the summary of what I want you to take away from this video is that, first of all, the arteries are serving as pressure reservoirs, primarily because they are so compliant. And number two, that the arterioles are changing blood flow by changing resistance, meaning the arterioles can constrict or dilate in response to a number of factors, including the sympathetic nervous system, metabolic factors, the endothelium, and other inputs that we'll talk about in a future lecture. So if you understand that, then you're all good for today. Thank you for watching, and I'll talk to you soon.